stress strain diagram for different materials, and what was of particular interest to us was this very steep linear section. Very steep by, I mean that these strain numbers on the x-axis are very, very small. We're still not in a large deformation zone, but the best part about this is, of course, that this is one linear, and it's retraceable. There's not what we call hysteresis. I think you've taken, some of you are in circuits or something, might have looked at hysteresis. Hysteresis is any curve that goes one way up and comes another way down, and then might retrace that shape again. We do not have hysteresis in this region. We go up this line, relieve the load, come right back down this line. That means it's very, very predictable, and the slope itself is a characteristic of the material, whether loaded or unloaded. It's no different than other type of numbers we have for materials like density. And we call this the elasticity modulus, the modulus of elasticity, however you want to put it. And it's the stress over the strain anywhere along that elastic linear region for the material. So we got our first look at that as a material property now, and it includes, of course, the actual deformation of some of the materials. This modulus elasticity you can look at in a way as the load on a piece, on a material, because don't forget that the stress is the force being applied divided by the cross-sectional area normal to the direction of that force that's absorbing that load. And then the strain is an actual deformation due to that load. So this is kind of like a ratio of load to response for a material. And this is the major design region in which we stay because of its predictability, linearity, and the like. And somewhere up along there where the linear portion starts to disappear, we call that then the yield stress. And that too is a characteristic of the material, how much stress that the material can take before it yields, because beyond that point the curve starts to come over and release the load, then we come down in a essentially parallel region, but now there's some built-in strain, even to the point where if we completely release the load, we still have residual strain. There's some permanent plastic deformation in the material now. The other number that was of some concern, and depends on what kind of curve we've got as to what kind of material we're looking at, but there was this peak or ultimate stress that's also characteristic of the material. For the most part, that's not a design region you want to go anywhere near, because once you're past that, then the necking starts, and sooner or later there's rupture of the material. Certainly, there's substantial plastic deformation if you've gone into that region, because now you're way out here in the strain. An awful lot of deformation has occurred by then. All right, so let's do a quick problem where we kind of use that business. So imagine a beam, 12-foot long beam, and this is a good chance for us to bring in something more to it. This is an I-beam in cross-section, which, believe it or not, is because it looks like an eye. We're going to be looking at a lot of these. These are generally come in a lot of predetermined cross-sectional dimensions, and you pick the type of beam that may be of best choice for your design. The beam designations are something like this. So this is this is the beam we're using for this. We'll look in a few weeks at just why an I-beam is such a strong configuration for a beam and so common in cross-sectional materials. The W just means it's a wide flange beam. And that's just a generic descriptor of the general shape of the beam. The 18 is the height of the beam, give or take a little bit. And the 97, if this is an English dimension beam, so this is a height of 18 inches, and the 97 is its linear weight, pounds per foot of beam. So if we have a 12-foot beam here, then we have 12 times 97 pounds as the weight of the beam. So we're going to take into account the weight of the beam. In this case, put it right dead center, and that's 97 pounds per foot times 12 feet is about 1164 pounds. Take that into account. Also, we're going to put some, imagine a small shear pad there and maybe about there. Yep, that's where I want to put them. And these we'll put about 8 feet apart. And that allows a couple things for this beam. One, it absorbs any of the up or down forces, just to give the beam a little bit of flexibility, but it also allows the beam to change shape thermally because of the great temperatures, the change in temperatures from use. As a beam like this might go through the year, the beam can change in length, and these shear pads can absorb that. We've got the beam there and the shear pad there. If the beam grows in length because of thermal effects, then the shear pad can absorb that by shearing over a little bit, and then when the thermal changes disappear, the pad can return back to normal, and the beam's nominally as designed. All right, so these are about 8 feet apart, and the center of the pad is about 4 inches in from the end. And we also have, just to spice things up a little bit, another point load of 40 kips. And that's about 40 inches in. So then it's about 32 inches over to where we placed the equivalent load representing the weight of the beam. All right, last little bit we need is a look at these shear pads themselves, because it's not enough for us just to look at the frontal area, because it's the whole area of the pad that's absorbing the shear. So the front that we can see there is 8 inches by 1/2 inch, but then the pad itself also goes back about 11 inches. So this part we see there is the same as the part we see there, the 8 inches by 1/2 inch. And then the beam rests on this whole top area that's 8 by 11, half the size of a sheet of paper. And the last little bit I think we need just for setup is that the modulus elasticity of the shear pad itself is 3,000. Remember what the units are? E is stress over strain. Strain is essentially unitless, so it's the same as the units for stress, which are units of pressure. Since we're working in English, this would be PSI. All right, so we want to find the compression in the bearing pads. The fact that this beam is is quite heavy is going to compress these pads a little bit. I want to find the compression in the pads, and because of that, the resulting angle of the beam. And as a designer of the rest of the structure, the angle at which this beam might be when loaded is very, very important, because it may make something else in the rest of the structure not work quite right. Okay. What we need to know, of course, is the force that's doing the compressing of these bearing pads. So if we call this NA and that NB, then we have some load there that's serving to compress that pad. And we want to find out what that compression is. Then the comparison of the two will allow us to find the angle of the beam once loaded. So let's see how we're going to get there. Let's see, the compression is part of the strain. So if we knew how much strain was in it, we know the original length that's being compressed, that's the 1/2 inch. So if we knew the strain, we could find then the compression. Well, the strain, the only other place strain comes from so far for us is in this modulus of elasticity. We know that for the pad, so if we knew the stress, then we could find the strain. Once we know the strain, then we can find the deformation of the pad. And the stress, of course, we can get from looking at whatever the load is and what's the area absorbing it. So the load we can find, that we could have done that last fall. That's just straight statics to find the load. Then we can find the stress. Once we have the stress with the modulus of elasticity, we can find the strain. Once we find the strain, then we can find the deformation. So, a real quick statics analysis. And we can find then the loads on the bearing pads, and then go up through this little chain of solution, if you will, this little trail that we can take, and we can solve the problem. I'll leave it as an exercise for you to prove that these loads are 27.1 kip at the left side and 14.1 on the right side. That's just from last fall. That's just statics, sum of the forces, sum of the moments, and you can solve for those two things. So continuing through then with with A, so the stress in bearing pad A will just be the load at A, which is 27 kips, 27,000 pounds, and then the area that's absorbing that load is which? Give me the dimensions, so make sure what you're talking about.
11 by 8 inches.
It's that area across the top of the bearing pad, the 8 by 11. 8 inches by half inch, no, sorry, 11 inches. Remember, don't put inch marks in an equation itself because it looks too much like a exponent. It's okay on a drawing because it's implied there. Sorry? And so I think that comes out to be, as usual, confirm my numbers, I think that's 308. So now we know the stress. We're given the modulus elasticity. Where does that come from? Yeah, that's generally supplied by the manufacturer. You may or may not want that tested. Depends upon your level of comfort with what the manufacturer's done. If you have a history with that company, you might trust them. If it's a brand new company, you might want to test a couple of those pads yourself. But that is a characteristic, a material characteristic generally supplied by the manufacturer. So now we have the stress, we divided by the modulus of elasticity. That'll give us the strain, and then we can get the deformation. So the stress we know to be 308 psi, modulus of elasticity 3,000 psi. Make sure you watch your units in all these problems, especially since we go through several of the levels of prefixes for the SI notation. That's a little over a tenth. 1027. 1027. It's unitless. Does that make sense? It does. If that's the strain, remember the strain is length of the distance of the deformation divided by the original length that absorbed the load, and now we can find out the deformation taking that strain. Oh, maybe I should have had little A's on each of these, just since we're doing the pad at A and then the exact same calculation through for the pad at B. So we know the deformation will be about 10% of the original length. And that's the half inch there. And so that comes out to be about 0.0513 inches. That's how much compression we'll find, we calculate at A. Now this is assuming that the compression is uniform over the bearing pad, that the beam stays level, which is a bit of an assumption, especially since we're admitting that we expect the beam to actually be at an angle, which would cause a little bit different compression on one side of the pad than on the other. And you're able to look at that once you finish the whole business. Plus there's another assumption in there that we'll get to. So you can do the same calculation for the other side of the beam, and you'll get the tilt there, about half of what was experienced on the left side. And then the tilt of the beam, we can just use those two. The difference of those two, I guess, divided by the entire length between the two, which is 108 inches. That's the 8 feet. That'll give us essentially give us the angle. It's actually the tangent, but it's a very small angle. Maybe I'll call it beta. And that comes out to be about 2.29 times 10 to the minus 4th radian. So it's very small. Might not be a worry, but you'd hate to find out after the building collapsed that maybe you should have paid some attention to it.
Why is it 108 inches?
Because what we're looking at here, if I draw it a little bigger, the beam was here, now it's kind of like this. So it's that distance. The difference between the two ends, because one end went down that much, the other one went that much. So that's this upper number here, and then the original length there, and so that's the tangent of that angle.
Is it 8 feet, 96 inches though?
Okay, I don't know where the 8 feet came from. That was a figment of my imagination. That's what that was.
9 feet?
God only knows. I think. Oh, is that?
That's 9 feet.
That's 9 feet. So I don't know. That's the number I used. I don't know. It's my garage, so I'll go measure it. Now, assuming the uniform compression on the pads, we get that angle. That's about a 7% error, ignoring the fact that the pads really, and I'll exaggerate this, the pads really deform non-uniformly across them. And we're assuming an average deformation and that the pad remains level. But it's a very small angle, not a very big error, and would be well under the factor of safety anyway. Thanks, Tom. Now, what we'll look at in a few weeks, near the end of the course, is further effects of this. Now, we're going to imagine that this beam dips by that amount. Of course, greatly exaggerated here. What we're also going to look at in the final weeks of the course is how the beam itself will deflect because of these loads. The beam itself will deflect something like this, again, very, very exaggerated, giving a different angle here than there is over there, and we'll also be able to take those into account as we look at that kind of deformation as well. We're assuming through this whole thing that this beam is rigid and does not itself deflect because of the transverse loads. It's just simply, we're just simply looking at the compression of the pads themselves. So there's actually two angular effects, and we're ignoring both of them at this stage. Travis, you're still frowning. Just stuck there. It's your Friday frown. Okay. So you double check that you got that number there. The rest is just trigonometry, figuring out how what the angle results in. All right. So we're going to sort of revisit something we looked at before. We just didn't do anything with it then. Imagine we have some solid. I'm going to need more space. We have some solid. Some material piece. We'll give it axes directions because we're going to have to refer to those here. So we've got some material piece there. Whether that's the entire beam or just an elemental piece of it is immaterial, because what we're worried about is the response to those loads that are applied. So imagine then an axial load is applied to this piece. As we've seen so far, that's going to cause the piece to elongate, but because the volume is the same, it's also going to contract in the other directions. So we might see a final heavily exaggerated piece that looks something like this under the load. Greatly exaggerated, the piece will elongate, but also contract. And not too bad for freehand at the board. Let me replace this force to illustrate it still applied at the end. All right. Okay, is that a helpful picture? See what happens? We did a problem where we briefly looked at this. In fact, we'll revisit that problem in a second. All right, so we have excuse me, an original unloaded shape. And then a resulting loaded shape. Again, greatly exaggerated. You can imagine if this was a rubber block that this kind of thing would happen. You can just stretch a rubber band, and if you look closely, you'll notice that it contracts in the other direction, orthogonal to the axial load. So we actually have a couple strains in the piece here. We have the normal strain in the x direction, which is how much it deforms in the x direction divided by the original dimension in that direction. So for our purposes, I guess it would be twice however much you drew sticking out here or out of the front. But there's also a transverse strain. This is axial or normal strain. There's also transverse strains in the other direction. The fact that there's a change in dimension in the y and in the z direction. And however much those are, of course, is going to depend upon the loads and the materials and a couple other factors. We're going to assume that the strain in the y direction is the same as that in the z direction. Since they are both transverse direction, it's arbitrary which one's the y and which one's the z. This means that we're assuming the material to be isotropic. In other words, it has no bias in terms of the direction the piece is actually loaded. It's the same in any direction. This is not like wood. Wood is very different in different directions for these kind of strains because of the grain of the wood. So wood has to be put down in a certain way. Steel is just poured into the shapes that are used. As you can imagine, the ratio of these strains is quite important. And this is called Poisson's ratio. Given the Greek letter nu, and defined as the lateral strains over the axial strains. We take the absolute value because, as drawn, these transverse strains are negative, the axial ones are positive for the picture I drew. And so this just makes the ratio a positive number, is all. Typical values for it, typically nu is less than about a half. Very common numbers are like 0.2, 0.3 for materials. And so we can actually use this calculation. We had this problem, I think, last week. We had an axially loaded piece that was originally 500 millimeters in length and 16 in diameter. (16 millimeters OD. OD means outside diameter. There's no inside diameter on this, but not atypical to do something like that. And then we showed, or I gave you numbers for the response to that loading. It elongated by 300 micrometers. So here's the 500, the elongation was 300 micrometers, but it also decreased in radius. Its original radius was bigger, and there was a decrease in the radius of 0.24. And that would serve for our del y and our del z in this radial direction. All right, remember that problem? Of course you do. We calculated the strains in the two directions. the axial strain is the change in length the 300 micrometers over the original length, 500 millimeters. All I'm doing is reproducing the same numbers we found earlier. So that has a strain of 600. And the radial strain, the transverse strain, the minus 2.4 micrometers over the original diameter 16. All right, so that's just brings us to the end of that problem that we finished. I think a week ago. All right, and then we can use that then to calculate Poisson's ratio by looking at the the transverse strains over the axial strains. Over 550 over 600, so about a quarter, 0.25. Or we expect for every unit of axial strain, there'll be about 25% of that will be the amount of transverse strain. So simple as that in calculation, simple as that to use. Not much more we could do with it. It is also, however, a material property, so you'd expect it to come from the manufacturer or from your own testing. All right, so as simple as that is, we'll take another step with it. We've got, well, let's see, we've got stress, normal stress, and shear stress. We've got strains, that was that departure from the, well, the first strains we had were the normal strains. Then we had some shear strains, which remember was the change in a 90-degree angle, whether imaginary or actual. Then we added the modulus of elasticity, which is something like load and response of the material. That was the first of them that was a material property. So we then added Poisson's ratio. Also a material property. And so we'll take it a little step farther and add a little bit to this list. So imagine we have some piece, whether this is an elemental part of a loaded piece or an actual part itself, and we see it undergoing some kind of shear. We looked last week why all of these must have the same magnitude and be oriented in that direction, or each one of them 180 degrees in the other direction. And the response of the piece might be something like that, and this angle here is half the shear strain, the other half being on the other side. And we define one more term. Let's see, we had the modulus of elasticity. That was the axial stress to the axial strains. We define the modulus of rigidity in the same way, only do it for shears rather than normal loads. So it's given the letter G, because there's a G in rigidity, I guess. And we can look at it in the same way. The load versus the response. The load is the shear stresses, and the response is the resulting angular strain. So we define the modulus of rigidity as something like that. In the same way we did the modulus of elasticity as load versus response. Again, this is also a material property. So just to kind of bring all these together, if you look in the back of the book, you don't have to, I'll put it up. We have, well, let me zoom out first, show the whole thing. In the back of the book, and this should be any strength of materials book, are tables like these. Ours just happen to be immediately in the back cover, so they're very easy to get to. We have English units on the first part of the page, and then the second part of the page, the very same thing in SI units. Down the right, we have different materials, different structural materials: aluminum, copper, cast iron, steel alloys, concrete, plastic, and even wood, different types of wood. And then across the top we have a lot of these material properties we've now been looking at. Specific weight is like density, only with weight instead of mass. Modulus of elasticity. Be careful of these units. All these numbers here happen to be in KSI. There's the modulus of rigidity. The yield strength is a number we're going to have to pay a lot of attention to. Notice for most of these materials it's the same in tension as it is in compression. Ultimate strength we're not going to use very often because we don't want to design out to that limit. Percent of elongation in a 2-inch specimen. I'm not real sure about that because I don't know if that's at the ultimate yield strength or the the ultimate strength or the yield strength. Then there's Poisson's ratio for all these materials, and they're all on the order of a third, somewhere in that region. And then coefficient of thermal expansion. We've talked about the thermal effects a little bit. I don't know that we'll actually get to any of those in the term, but they're pretty straightforward, as you imagine. You have a delta T, a change in temperature from unloaded to loaded conditions, and then you figure out how much expansion in the piece as a ratio, just like the strain is. So it's a fairly straightforward number. So you gotta be careful. Watch out with the units as much as anything when you use these numbers. Okay, we'll do a quick problem then using some of these new things we just got. Now we've got this whole table. Some of them are just the loads, but then some of them are material responses to those loads as material properties. All right. Okay. So let's imagine we have a shear block. A shear block is an elastic, maybe a polymer of some kind, like rubber, that can absorb shear loads on them. So imagine we have a rigid plate on each side of this with the shear block in between. And we'll assume it's rigidly mounted to some surface, and then there's some kind of load here that then causes the shear block to deform, and it might do something like this. That'll cause this plate to come out some length because of the shear response of the shear block. And it might do something like that. If we look at it on the side, as that upper plate is subject to some kind of load that causes the entire shear block to deform, to absorb that load, something like that. The reason it's a curve shape like that is because the bonding of the shear block to the plate would cause the block to actually have no slope to it there, and then the entire center section is absorbed by the slope, or absorbs the load. So let's see, given a couple things here. Depth of the block 50 millimeters, length 160, height 40, all those in millimeters. The modulus of elasticity, and you can see how they painted it right on the side here. (600 megapascals). And this maximum deformation here is 0.8 millimeters. That's the same thing I drew down here inside view. Okay. So, I want to find a couple things. Find average shear strain. What do I mean by average? What assumption do you make seeing that word average? We don't worry about the fact that the strain varies with location along here, because remember, strain is the angle in the material, and it's very different at different points. So just assume then this average deformation And that's then simply the angles there. The angle there is 0.8 over the original 40, I believe. Make sure I wrote that number down right. So that's very straightforward. I'm going to give you something else. It's a little bit more involved now that we have that. Because that's just the response of the material. Now I also want you to find the load P that caused that response in the material. It's the load P that's causing the shear. It must be balanced on the other side for static equilibrium. There's also obviously other things going on to resist the moment that those cause the couple. But that's the mounting of it to rigid plates that will supply that. We're not looking at that in particular. So the shear must be that load over the area that's absorbing it. We can find that because we know the modulus of the rigidity. So that will come from the fact that we've been given G. We just calculated the strain. We can find the shear. Once we find the shear, we can find the load. So I'd like you to do that. As much as anything, the difficulty is just making sure you've got the right area in the calculation. There's a lot of shapes and distances and numbers here. You've got to make sure you've got the right one. So that's your task for a minute or two. Got a lot of areas in these problems. We've got to make sure that we actually have the right area in the calculation. A lot of areas, a lot of dimensions, a lot of changes. Lots of units. Make sure you're all getting the same numbers. Lots of large SI numbers in here, megapascals, kilo. Even, I think we come across giga a couple times. A number? Not in the mood? Not on an optional day. Don't carry too many sig figs. Remember, we're going to have a huge factor of safety on all this. Two, these are all just, they're just everything here is based upon experimental values. Notice that this, David, was a big round number, 600. So to take the answer to any considerable precision doesn't really match what you've got going in. You've got pretty approximate numbers going in.
It would be unnecessary.
Yeah, you don't need that kind of precision coming out.
Okay.
And you have to be careful about that, because if you send a dimension drawing down to manufacturing in your company, and you have an extreme precision on it, because there's so many sig figs, they'll try to build it to that, and they'll charge you for that effort. And if you put a lot of precision in, it takes a lot of machining expertise to finish that, and they'll bill you for it. So we can find the shear stress, and then we can find the load from the shear stress, as long as you have the right area in there. What do you have for the shear stress? Everybody got that number? Boycotting? 12 what? Megapascals. Which is what we had on there. So you're going to be really good with the SI prefixes in this class. And now we've got the shear. What area did you use to absorb that shear? Travis, what did you use?
160 millimeters and 40 millimeters.
100. So that's this side there. Chris? This shear is, it's actually, it's all along the top of the piece, so you have to use the 50 by 160. And then you have to watch your units. So the area is this entire top area there, because that's the area that's absorbing that shear stress. And you get for that 96. What units? Kilonewtons?
I believe so. I thought it was negative.
Don't forget these are all in millimeters here, so that's a total of 10 to the minus 6 right there.
Yeah.
So it should be 96 kilonewtons. All right. All right, a couple problems kind of wrap up what we've done in this chapter, because this pretty much ends chapter 3. So let's see, maybe we'll do a big one and then get out of class one. All right, we'll use some of those things that we just had. We won't use all of them, but that's up for you to decide. A lot of stuff here in chapter 3. So again, a loaded beam held by 2 supports. Different lengths. This one's 220 millimeters. This one's 210, 10 millimeters shorter. Each of those supports are the same. Both of them are 2014 T6 aluminum, which is in the book. At least I believe it is. Let me double check real quick. Yep, it's there. So you can look up any of the material properties you might need. The beam itself is rigid and 3 meters long. There's an 80 kilonewton load. And the design criteria, let's see, I'm missing a number here you need. Oh, wait a second, I'll get you going. The design criteria is that under this load, the beam must remain horizontal, which means it must be placed carefully at the right location. If it's too far to the left, then this support will compress too much, won't be horizontal, and vice versa if it goes to the other side. So, now if we did that in statics, oh, there's the number I was looking for. I did have another. Both of these are 30 millimeters OD. Circular cross-section. Now, we could have we could have done something with this problem in statics. However, all we would have come up with in statics, maybe we'll call it the pure statics solution, because we're still in a statics course, but now we're looking at deformable solids. The pure statics solution would have done nothing more than told us that the loads should be equal and the load itself should be in the middle of the beam. That's all we would have gotten if we'd done pure statics. That's not going to work because if there's an equal load in the two of these, one of them will deform more than the other. Which one? If the loads in both of these struts were the same, which one would deform more, and then the beam would not be level? The longer one, because remember the strain has to do with the original length. This one's longer. Under the same load, it'll strain more. So we actually have 4 unknowns. Of course, the reactions in the struts, but we also don't know where to place the load yet. What's the 4th unknown? There's actually a 4th and a 5th, but they're equal, if that's a hint. What is the compression? What is the response of these struts to those loads such that the beam remains level? So del A equals del B, but both are unknown. So of course we need 4 equations. What are those 4 equations? Well, it's a statics class, so the forces better sum to 0. The moments had also better sum to 0. In fact, you're going to have to do that 2 times. I'm not sure of any other way to do it, but do the moment, sum of the moments about each end. So that's 3 equations. Then the 4th equation is actually this one here, where the deformations themselves are the same. And that's something we never had in statics. But now that we're looking at the deformable solids, we do have that kind of thing as a way for us to solve these problems. In statics, this would have been an indeterminate problem. More unknowns than we had equations. Remember, we only have 3 equations in statics. Now that we have the deformations, we have other ways we can make these calculations as needed. So take a few minutes and come up with where we should place the load and what the deformations are. At least set up the equations. They're actually not that difficult to solve, really. Sum of forces is that. Then you can do the sum of the moments about each end. Each one of those will eliminate one of the knowns, or unknowns, and have the other. And this stress, the deformation equation, actually takes a slightly different form. Which would look something like that. Since they both have the same cross-sectional area, we don't need a subscript on that. For each of the 2 deformations, we know from our definition of E, stress over strain, that we can then solve for the deformation as those. That'll give you 4 equations and 4 unknowns. You can actually, I believe, yeah, you can get X right from this one. Well, no, not right from it. Actually, the 2 moment equations will go in there. When you write the moment equations, one of them will be in terms of FA, one will be in term FB, and you make that substitution. The F's cancel, leaving just the X. Then you can go back to either equation and get the forces in. So set up the moment equations, put them in here, and we'll leave it at that, because after that it's all just algebra. Make sense? All right, set up the 2 moment equations. That'll be one in terms of FA, one in terms of FB. You can put those both in. Then actually solve for the remaining, solve for the X from that. Make sense? A little bit? When you set up either moment equation, okay, good. Looks like everybody's getting the pieces of it. Sum the moments about A. We know that the moment caused by the load must be opposed by the moment caused by B. And that's 3 meters. So there's your first equation. Solve that for FB and put it in the deformation equation. How'd you get those? How'd you get, what's this, 10.6? Oh, that's the elasticity? Well, I don't know. Oh, John.
Is it 2014?
You're no longer my favorite student.
Why?
Because of what you did. I'm sorry, you cannot claim that status. And then the moment equation of B,
Oh, I see.
what'd you do? That's all
73.
here. What?
I
Yeah,
was
wrong page, English units, right?
I'm English. What do you want?
It's a flat world out there. Which means you need to be cognizant of all systems and cultures.
Friedman.
And the 6th Pascal. And the ratio, sorry, Poisson's ratio, 0.35. Want that because I want to find the final diameters. I hadn't put that up yet, but that was one of the things to look for. The final diameter. And you'll need Poisson's ratio for that once you find the axial load, the axial strain. So each of these can go into there. That'll give you a single equation in X as the only unknown. All those other quantities are known.
But I don't get why you want to do 2 moments.
Yeah.
Aren't they dependent equations?
Aren't they dependent?
They find each other, aren't they the same thing?
Not with X is an unknown. You can't use them to solve for either one, and you can't use the 2 to solve for either one. That's the difference, because this X remains an unknown. This is 2 equations, 3 unknowns. So they're not dependent equations, they're independent in this case. If we didn't take into account the deformations, then they are dependent equations, but you'd only need one to solve for either of those anyway. You'd use the sum of forces and the sum of the in one of the moments. Maybe is there another way to do it? This is
I shouldn't use second moment.
yeah. Because when you put it in here, then you have your third equation. Oh, gonna have to make this the get out of class question, I guess. Or come into class question on Monday. We actually start a new chapter though. Work? Did you do it?
Yes, I use actually algebra.
That's X.
Yeah.
And
I finally got this
it's I have so it's going to have to be a little bit past halfway because of the extra length on A. There's not a lot of extra length, but a little bit. So it's going to have to be a little bit past past the midpoint. We're getting right near the end, so I'll give you the answers. You double check you can get them. This should all lead to x equals 1.53 meters. So it's only barely past the midway. You got that too, Chris? Good. Once you've got that, you can go back into these first two equations and get the loads. As 39.1 on A. And then, of course, since the total load is 80, what's that, 40.9? So not a huge difference. Make sure you can get those, and then I'll leave it to you to come back on Monday with the final diameter of leg A. You could do either leg, but it's the same calculation. And you'll need Poisson's ratio for that.